Welcome to the week 3 of the course Basics of Mechanical Engineering 3. We are discussing the thermodynamics and fluid mechanics in this course. Professor Ramkumar has covered in the first 2 weeks an introduction to thermodynamics, and also we have discussed in detail the laws or the basic laws of thermodynamics. This is a tutorial session that I will take on introduction to thermodynamics, where I will discuss some problem statements based upon the relationships that you have learned in the week 1 and 2. I am Dr. Amandeep Singh Goborai from IIT Kanpur. Just to recall the concept of kinetic interpretation of temperature, this is the relation that we have. The kinetic energy arises from the motion of particles, vibration in solids, sliding in liquids, and free motion in gases. Average kinetic energy per particle is directly proportional to the absolute temperature. We have temperature here, it is directly proportional here, and the relation is given by 3/2 kT, where K is the Boltzmann constant, and this value of K is 1.38 into 10 raised to power minus 23 joules per Kelvin. The lowest theoretical temperature, that is absolute zero, which is 0 Kelvin, corresponds to the zero kinetic energy, where molecular motion would theoretically cease. This is just the recalling of the concept. Let me directly come to a problem statement. It is a very simple problem statement where it is mentioned that the average kinetic energy of a molecule in air at room temperature at 25 degree is to be determined. We have been given here temperature as 25 degrees centigrade. To convert this into Kelvin, conversion into Kelvin scale, it is only we add 273 degree over it, that is it turns out to 25 plus 273, which is equal to 298 Kelvin temperature. Now we know the value of small k, that is the Boltzmann constant, that is 1.38 into 10 raised to power minus 23 joules per Kelvin. Now let us use the relation that we saw in the previous slide. Kinetic energy average is equal to 3/2 kT. This is equal to 3/2 into 1.38 into 10 raised to power minus 23 into the temperature, that is 298. 25 degrees is the standard temperature pressure system. So here the kinetic energy is 6.1686 into 10 raised to power minus 21 joules. This is the very first problem statement of the course, and I have kept it the most simple. Now let us see or recall the concept of internal energy. Internal energy refers to the energy contained within the system. The energy represents the overall energy of the system. In the overall energy, we have potential energy and kinetic energy both. So we have potential energy that is stored. We have kinetic energy based upon the movement. Total internal energy for the two particles, it is shown here. In a chemical reaction, we know about energy transformation, and basic thermodynamics provides us with information regarding energy change associated with particles of the system. This energy change is the change in internal energy. It is the total energy within the substance. It is the sum of many types of energies like vibrational energy, translational energy, etc. The absolute value cannot be determined, but experimentally we can find the change in internal energy, that is delta U is equal to U2 minus U1. Also, this change in internal energy is the difference between heat added to the system and work done by the system. Work is done on or by the system, or matter enters or leaves the system, heat passes into or out of the system. So the change in internal energy of the system is equal to heat added to the system minus the work done by the system. Using these relations, let us now try to see a problem statement where it says gas absorbs 160 joules of heat from its surroundings and does 80 joules of work, which means 160 joules here is the Q. Q is 160 joules. 80 joules of work is done. That means work done is 80 joules. If the final internal energy is 30 joules, then what is the initial internal energy of the gas? Now, out of U2 and U1, if I try to make a small illustration for this, let us see it in this way. We have a gas here and we have initial and final internal energies. And in this system, we have heat coming in and work is done from the system. I could say it enters here, it goes and then it goes out. So here this is U1, that is initial internal energy, which is to be determined. We know U2, that is 30 joules. We know work done, that is 80 joules. We know the gas absorbs 160 joules of heat from surroundings. So that is Q, that is heat entering the system, is 160 joules. So this is gas, and outside here we have atmosphere, from where this energy enters here. Now let us find the initial internal energy. We know U2 here is given as 30 joules. That is the final internal energy. Let us put the relationship of delta U, which is the difference between the heat entering the system and work done by the system. This is equal to 160 minus 80. This is equal to 80 joules. And this internal energy change is also equal to the difference between the final and the initial internal energies. So that means 80 joules is equal to 30 minus U1. We get the value of U1 as minus 50 joules. So there could be some problem statements like this in the activity questions. There could be some problem statements in the exams or maybe in the quizzes. So these are very simple problem statements just trying to relate to the system. Next, I will come to the topic revision of the temperature scales conversion. This is also very commonly used transformation systems, and this is very important to learn. Around the world, various fields and regions utilize different temperature scales for measuring. This is all discussed. Only these scales, F minus 32 by 180, the difference, C by 100, K minus 273 by 100, R by 80 for the Fahrenheit, Celsius, Kelvin and Raymond scale. These relationships are already discussed. Let me come to a problem statement. Convert 113 degrees Fahrenheit to Kelvin. So we have been given temperature in Fahrenheit, that is F equal to 113 degrees Fahrenheit. Now we know the relation between Fahrenheit and Kelvin, F minus 32. This by the difference between the boiling and the freezing temperature, that is 180 degrees. This is equal to K minus 273. Here we also take to the denominator 100, that is difference between the boiling and the freezing temperature of water. This gives me K is equal to 100 into F minus 32 by 180 plus 273. That means K is equal to, putting the value of F, that is 113. I get the Kelvin temperature as 318 degrees Kelvin. So this is only one conversion. There could be problems where we need to convert Fahrenheit to Celsius or maybe Fahrenheit to Reamer scales. Commonly used scales are generally Fahrenheit, Celsius and Kelvin. Now let me come to the laws of thermodynamics. First law of thermodynamics. There is isochoric process, there is isobaric process, lot of processes we have discussed in the week 2. To discuss about the isochoric process, that is a constant volume process. An isochoric process is one in which the volume remains constant throughout the process. Key characteristics are any heat added or removed changes the internal energy and pressure, but the volume remains constant. No work is done since the volume doesn't change. Examples are heating of gas in a sealed or rigid container. The volume of the rigid container remains same, but like your LPG gas cylinders at home. Combustion of fuel in an engine cylinder before the piston moves. Those are metallic parts. The volume is 100% fixed. There is no change. Pressure increase in a pressure cooker before the safety valves operates. These are the examples of isochoric process where the volume remains same. That is, V initial is equal to V final. However, the pressure varies. Now, isochoric means constant volume process. For a reversible constant volume process, Q is equal to delta U, which is equal to m dot into Cv into the change in temperature, where m dot is the mass flow rate, Cv is specific heat at constant volume, and T1 and T2 are the temperatures at inlet and outlet of the system. P1 and P2 are pressure at inlet and outlet of the system. Here the work done is 0 because no volume change. In PVT relation, P1 by T1 is equal to P2 by T2. Using these relations, let us try to see a problem. A steady flow system is operating with air as working fluid. The air undergoes a reversible process at constant volume. That is, we are talking about isochoric. The mass flow rate through the system is 1.3 kilograms per second. At the inlet, the air has pressure of 1 bar and temperature of 290 Kelvin. At the outlet, the pressure is 3 bar. Assuming air behaves as an ideal gas with a constant specific heat at constant volume, that is, Cv is given as 0.718 kilojoules per kg Kelvin. Determine the rate of heat transfer. Rate of heat transfer is to be determined, that is, heat exerted for this process in kilowatts. Here, as you saw the figure in the previous slide, we have constant volume. This is volume here. In the x-axis, in the y-axis, we have pressure. Pressure is in bar. It has been given here m dot, that is the mass flow rate, it is in kilograms per second, as 1.3 kg per second. P1, the pressure is 1 bar at the inlet, and temperature here is 290 Kelvin. P2 is 3 bar and Cv is also given as 0.718 kilojoules per kg Kelvin. The volume is constant. There is an initial pressure, that is 1 bar. There is final pressure, that is 3 bar. So this is P1, P2 level, and here correspondingly we have T1 here and T2 here. Now first calculating T2 so that we come to calculate the heat exerted. Heat exerted would be taken through this relation Q, and we need m dot Cv, T2 and T1. Here T2 is missing. So to come to this relation, that is Q is equal to m dot into the specific heat at constant pressure times the difference between the final and the initial temperatures. I need to find T2. That means T2 is to be calculated. To find T2, I will use the relation P1 by T1 is equal to P2 by T2. Now putting the values here, that is 1 by 290 and P2 is 3 is equal to 3 by T2. This gives me the value of T2 as 290 into 3, that is 870 Kelvin. So, because the volume is constant, because of the rise of the pressure, the temperature too is 870 Kelvin, and here the temperature was 290 Kelvin only. The pressure 1 is 1 bar, this is pressure 2, the final pressure, that is 3 bar. Now, heat exerted for the isochoric process. So, now we can put values here. M dot is directly given 1.3, value of Cv is directly given 0.718, and T2 minus T1 could be put here as 870 minus 290. So, this gives me 1.3 into 0.718 into 580. This gives me the value of the heat exerted for isochoric process, that is 541.37 kilowatt. That is heat exerted for isochoric process, that is constant volume. Now, the other process that was discussed is isobaric, where we have constant pressure. And isobaric process is one in which the pressure remains constant throughout the process. Here we have pressure versus volume. You see here the volume varies from V1 to V2, but the pressure remains constant. Key characteristics are volume and temperature may change, common in systems with movable boundaries such like pistons. Earlier I talked about the LPG cylinder, which is a closed system. Now, piston and cylinder system is moving. The cylinder is closing and opening. So, the volume is changing here. Some of the other examples which are given are boiling water in an open container at atmospheric pressure, heating in a piston cylinder assembly with a freely moving piston, steam generation in boilers operating at constant pressure. At constant pressure, the volume is changing. Here, when we saw the reversible constant pressure relationship, here the heat that is generated is equal to H, which is equal to m dot into Cp into T2 minus T1, where Cp is the specific heat at constant pressure, which is also in joules per kg Kelvin. And work done here is the integral of PdV, that is pressure into the change in volume. This could also be put as mR into T2 minus T1. In the PVT relation, V1 by T1 is equal to V2 by T2, because the pressure is constant here. Let us see a statement and try to find the solution to the questions given here. Air enters a steady flow system at a pressure of 2 bar and a temperature of 300 Kelvin. It is heated at constant pressure until its temperature reaches 600 Kelvin. Now, here I will again draw a figure. They say air enters a system at a pressure of 2 bar. The pressure here given is 2 bar. And they said the temperature here is T1 is equal to 300 Kelvin. This is a constant pressure system. Heat is heated at a constant pressure until the temperature reaches 600 Kelvin. That is the temperature 2, T2 is equal to 600 Kelvin. But this is at a constant pressure. So, if I draw this relation, pressure versus volume, here the pressure remains constant, but the volume varies. So, this is pressure, we call it as pressure P, that is 2 bar, P1 or P2, whatever you call it, it is 2 bar. I need to call it at P only. P1 is not required. So initial and final volume and initial and final temperature as well. We have T1 here and T2 here. Temperature 1 is 300 Kelvin, temperature 2 is 600 Kelvin, volume V1 and V2. Let us see. The mass flow rate is 2 kg per second. That means m dot is equal to 2 kg per second. Assume air behaves an ideal gas with R is equal to 0.287 kilojoules per kg Kelvin and Cp, that is the specific heat at constant pressure, is equal to 1.005 kilojoules per kg Kelvin. Calculate number 1, the rate of heat transfer to air. To find the rate of heat transfer to air, I will start calculating this as well. Calculate number 1, the rate of heat transfer to air. Number 2, the rate of work done by the system. Number 3, the ratio of final to initial volume. To cater the first question, that is part 1, they are asking the rate of heat transfer. I will use this relation, rate of heat transfer Q, that is equal to H is equal to m dot into Cp into T2 minus T1. These all values are given. I will put the values, m dot as 2, Cp as 1.005. The difference in the temperature, that is 600 minus 300. These are all given in Kelvin. This give me the value of the Q or H, that is rate of heat transfer, as 603 kilowatt per hour. Second question, that is rate of work done by the system. Rate of work done by the system, I need to find value of W. To recall, the work done is equal to m dot into R into T2 minus T1. The value of R, m dot, T2, T1, everything is given in the question. You could see m dot is this, value of R is 0.287 kilojoules per kg Kelvin. Let us try to now put this relation, rate of work done that is W is equal to m dot into R into T2 minus T1. This is 2 into 0.287 times the difference in the temperature, 600 minus 300. This gives me the rate of work done as 172.2 kilowatt per hour. Now, third part. They have asked the ratio of final to initial volume. Final to initial volume, that is, I need to find V2 by V1. This is to be found. We know in PVT relation, we have V1 by T1 is equal to V2 by T2. That is, we are talking about isobaric process. Isobaric means here bar, that pressure is iso, that is constant. We have here V2 by V1 is equal to T2 by T1. That is ratio of the final volume to the initial volume. This is equal to 600 by 300. That is equal to 2. That is V2 by V1 is equal to 2. Hence, all solved. One more topic I will cover in the first law of thermodynamics, that is the polytropic process. Polytropic process is a thermodynamic process that obeys the relation PV power n is equal to C P is pressure, V is the volume, N is the polytropic index, C is the constant. The polytropic index will take any value between 0 and infinity depending on the process that is under discussion. Work done in polytropic process is also discussed, that is P2 V2 minus P1 V1 by 1 minus n, where P V power n is constant. The exponent n defines the type of process, that is n0 is isobaric, n is equal to 1 is isothermal. So in thermodynamic processes, n is equal to 0 is for complete isobaric process, that is pressure is constant, n is equal to 1 is the isothermal process. In between we have a polytropic process, and isochoric process is when the volume is constant, that is n is equal to infinity. Now let us see this problem. It says a mass of 8 kg gas expands within a flexible container so that the PV relationship is of the form PV power 1.2 is equal to constant. The value of n is 1.2 here. N is equal to 1.2. The initial pressure is 1000 kilopascal. Initial pressure, that is P1 is equal to 1000 kilopascal. And the initial volume is 1 meter cube, that is V1 is equal to 1 meter cube. The final pressure is 5 kilopascal. Final pressure, that is the reduced pressure, is 5 kilopascal. And the specific internal energy of the gas is decreased by 40 kilojoules per kg, that is delta U is given. It is specific internal energy they are talking about, that is small u, delta small u is equal to 40 kilojoules per kg. They say it is a flexible container, the key word. If there is a container that carries some mass, this finally would be a bigger container, or just make it something like this, where the pressure is drastically reduced. So here, suppose in a container we have some mass of the gas. So here, suppose in a container we have some gas. For the gas, I will just draw dots. So this is expanded here. Initial pressure is given as P1 is equal to 1000 kilopascal. Final pressure P2 is equal to 5 kilopascal. From initial to final it goes with the mass as 8 kg, that is given, and change in specific internal energy as 40 kilojoules per kg. So this is initial and this is final. So I can put here as mass is also given 8 kg. So all the given values are put here. Let me try to find what it has asked. Find the heat transfer. To find the heat transfer, I will first find change in internal energy, that is delta U. This is delta capital U. It is not specific internal energy. This is equal to mass times the change into the specific internal energy. This is equal to, the mass is given 8 kg, and this change in internal energy you could see is negative. So I will put it as minus 40, because you see the volume here is increasing. So they say is decreased by 40 kg. So I will put this is decreased, that is it is negative. So 8 into minus 40 turns out to be minus 320 kilojoules. That is a change in internal energy. Now heat transfer, as we know, delta U is equal to Q minus W. So I will put it as Q is equal to delta U plus W. So I get heat transfer as this. Now I need to find W here, that is the work done. This is equal to, given in the relation, P2 V2 minus P1 V1 by 1 minus N. This is P2 V2 minus P1 V1 by 1 minus N. Now here we know that PV power N is constant. That is, we are talking about the polytropic process. So that means P1 V1 power N is equal to P2 V2 power N. This gives me V2 by V1 power N is equal to P1 by P2, and V2 is equal to P1 by P2 power 1 by N into V1. That means V2 is equal to, the value of V1 is 1 meter cube, that is volume given here is 1 meter cube. So I will put this as 1. P1 by P2, I can also put the values. P1 is 1000, P2 is 5. This power 1 by 1.2. This into 1. This gives me the value of V2 as 82.4 meters cube. Now using this relation here, I get the value of W as P2 V2 minus P1 V1. P2 V2 is 5 into 82.4 minus 1000 into 1 by 1 minus N, that is 1 minus 1.2. So the value of work done here turns out to be 2940 kilojoules. Now finally we need to find the heat transfer here. That is, heat transfer is given here. Q is equal to delta U plus W. That means Q is equal to minus 320 plus W value is calculated 2940. That is, Q is equal to 2620 kilojoules. This is the answer. So these were a very few simple and little calculative problem statements on the first law of thermodynamics. I will discuss about heat engine, heat pumps in the second part of the tutorial session, which is based upon the week 1 and week 2 lectures in the coming lecture. Thank you.